Thanks a lot, Jeroen and Matthias, for inviting me to come here. So yes, so I'll talk about some joint works, which was, I mean, the core mathematical presentation. I will present it in terms of Shannon capacity of hypergraphs, but for me, the motivation came from a problem in communication complexity that I looked at a long time ago, and I was hoping that recent progress in tensors, for the capset problem, for example, would help for this problem. As you'll see at the end, it didn't really help for this problem, but in the course of this project, we made some observation that I would like to share with you here. So yeah, and this is joint work with Matthias and PhD student, or my former PhD student, Wangta, and Jeroen. I hope I'm getting it correct. Yeah. Okay, so maybe let me start with the plan. So what I'll start with is first the setup. What do I mean by Shannon capacity of hypergraphs and the motivation? So here I'll try to describe the communication complexity motivation. And so yeah, maybe let me mention it. So already here, for those who know, so that we'll talk about the corner problem here. And its connection to number on the forehead, communication complexity. And okay, and so yeah, the Shannon capacity of the hypergraph is a number, and so I'll separate my talk into two parts. The most interesting part is usually the upper bounds, but the place where we could make real progress is more on the lower bound side. So I'll start with that. And upper bound. And this will be more like on barriers. So this is the overall structure that I'll try to follow. Okay, and so let's start with the setup. Yeah, I'll start with the setup. What do I mean by Shannon capacity of hypergraphs? So let me just define things one by one. So a K hypergraph, which I will note by G times E. Okay, so this is like a finite vertex set, and E will be a subset of V to the K. Okay, so it's so here I take ordered, what we can call ordered hypergraph. So it's really arbitrary K tuples of vertices. Okay, I can even have the same vertex several times. Okay, so yeah, let's consider some examples. Okay, so I'll start with what I'll call the capset hypergraph, which will, as you expect, it will be directly related to the capset problem. So this is a very simple hypergraph. It just contains 3 vertices, and I consider the tuples where I have all the 3 vertices. Okay, so we can draw it this way if you want. Okay, so here V is just 1, 2, 3. Actually, you should maybe call it 0, 1, 2 if you want to make the connection to capsets more transparent. And E will just be all the permutations of 0, 1, 2. Okay, so I have 6 edges. Okay, and it's all the possibilities of which contain 1, 0, 1, 1, and 1. Okay, 0, 1, etc.
You add the 0, 0, 0 and the 1, 1, 1 and 2, 2, 2 or not?
Yeah, so I didn't take the convention of putting in the edges the self loops, but yes, this is an important point, is that when we'll do the adjacency tensor, we'll add these loops. So okay.
Yeah, so K hypergraph is just the support of K tensor. Also, right?
Sorry?
One way of thinking about a K hypergraph is that it's the support of a K tensor.
Yes, yes. I mean, yeah, the only thing is that usually I'll assume the diagonal to be all ones. That's what I call a hypergraph. Otherwise, maybe it's less clear. But actually, yeah, all the things that we'll see in this talk apply equally well to any tensor. I mean, I just thought that presenting it in terms of hypergraph might be more intuitive. Okay, so this is what I call an undirected hypergraph. Okay, and so, and this is, I think, the maybe most common definition of hypergraphs is usually undirected, but I want to here we'll have some directed hypergraph in the sense that if I have a tuple here, I don't necessarily have all its permutations. Okay, so for example, yeah, just another example. So I can take v equals of 0, 1, 2, and take the corresponding edges to be, let's say 0, 1, 2, 1, 2, 0, and 2, 0, 1. Okay, this is an example of a directed hypergraph. Okay, good. So now let me move to the adjacency tensor. A of G, it's like this for a hypergraph G. Okay, so in the rest of the talk, I'll assume K equals 3. Okay. Okay, most of the things generalize to other Ks, but simplify the notation. Okay, so A of G is a 3 tensor, okay, where I put the 1 if I have an edge, if I1, I2, I3 is an edge, or I1 equals I2 equals I3, okay, and 0 otherwise. Okay, so this adding this will be quite useful when we take products. Okay, and so this is just a way of representing hypergraph. Now, an important quantity, so the Shannon capacity will be a property which is related to the largest independent set of a hypergraph. And so let me define what I mean by an independent set. Okay, so this is a subset of vertices that satisfies the following, that for any I1, I2, I3 in S, I1, I2, I3 is not an edge. Okay, and I use the usual notation alpha of G to be the size of the largest independent set. So, okay, so yeah, just as an example. So alpha for the cap set. Okay, so if I take any 2 vertices, for example, 0 and 1, then this is a valid independent set. And so, of course, if I take the 3 of them, it's not an independent set. So alpha is 2. Okay. Okay, and so now I come to the Shannon capacity of a hypergraph. It's the asymptotic growth of the largest independent set as I take tensor powers of my hypergraph. Okay, so this, I mean, the wording Shannon capacity was defined, is used mostly for graphs, but here I took the liberty to define it also in general for hypergraphs. Okay, because I mean, it's called Shannon capacity because Shannon is the one who studied this first, motivated by communication problem in the 0 error setting. Okay, so here, Shannon capacity. Yes.
So does it have like an interpretation in terms of capacity in case greater than 2? Or
yeah, no, not that I know of. Yes, interesting question. I tried to think about it, but I didn't manage to find an interpretation. Yeah, so for graphs, it does have a very natural interpretation in terms of like an edge is if 2 symbols are confusable. For a hypergraph, I don't know of interpretation. Could be, but I don't know interpretation. Okay, so yes, so let me define, for that I need to define the product. Okay, so denoted in this way. So I take 2 hypergraphs, 2 K hypergraphs. So this is a hypergraph with its vertex set is just Cartesian product, and the edge set, H is equal to the set of I1, I2, I3. Yeah, so either both. So if yeah, maybe I should have yeah. So it's I1, J1, I2, J2, I3, J3, such that the following holds. I mean, if you think of in terms of adjacency tensors, it just corresponds to taking the tensor products of the adjacency tensor. But let me write it like this. So I1, I2, I3 is an EG, and J1, J2, J3 is an EH. Okay. And I have these two things. Okay, but this is not the only condition. Yeah, given that I took the convention of not putting the self loops here. So so I have an edge if this happens, but also if in one of the two cases I have 3 times the same. So I1 equals I2 equals I3.
Against it.
Yeah. And yeah, here the same, or I1, I2, I3. This will be G and J1, J2. Okay, and so the maybe in terms of tensors, I think the best way of seeing it is just as G. It's just the product, the tensor product. And again, it's understood exactly as in the in Tobias' talk, where I mean this is a 3 tensor, and this also I understand it as a 3 tensor. Okay, and so the Shannon capacity, so denoted by theta, of some graph G is equal to the limit as n goes to infinity of theta.
Let's put an alpha then. Where you
So yeah. Oh, yeah. So alpha of G n. Okay, so as n grows, in general, this can be super multiplicative. And so the question is, how quickly does it grow? Okay, and as you might know, this is for k equals 2. This is well studied, and this has an interpretation in terms of zero error coding. And this is a question even that was posed by Shannon. He started the study, and so one of the the landmark result there in this area is the fact that theta, you take C5, so the cycle of length 5, this is equal to square root of 5. Okay, and this is a very famous result by Novas in 79, I think. Yeah. And yeah, for doing this, he introduced his famous Lovász theta function, and he solved this problem. Okay, so so yeah, he introduced the Lovász theta function as an upper bound here. So what you need is an upper bound on the independence number here that is multiplicative under this strong product. And the Lovász theta function is exactly doing this. Okay, now, yeah, then thing is for k equals 2, for k equals 3. Okay, so we have much less methods. So we do have some methods which are based on the rank. Okay, so yeah, maybe before going to k equals 3 and k equals 2, yeah, so there's the Lovász theta function, but there's also, you can use rank-based lower bounds because the rank of tensor products of matrices is multiplicative. So you can use the rank as to give upper bounds on the Shannon capacity. In the for k equals 3, there are some rank methods, which is what people used for the capset problem. But in general, there's let's say much less method. Okay, so this is the general picture about Shannon capacity. Let me now get to the motivation. Okay, so why would you care about the Shannon capacity of hypergraphs? And I want to tell you that actually many of the like quite natural problems in extremal combinatorics can be written in this language. Okay, especially if you look at things on a group which has a product structure, right? Which is the family of groups is obtained by taking some basic group and you take it to the power n. So for that, so yeah, I started with the capset. Okay, so the capset problem. So I want to tell you that this is exactly a Shannon capacity problem for this hypergraph. So what is the capset problem? It's just you want to find a subset of Z3 to the power n. So it's a capset, so it's a capset. Okay, if it doesn't have arithmetic progressions of length 3. Okay, so what does that mean? So if for all x, y, z in S, we have the two things are equivalent. So x plus y plus z equals 0 implies that x is equal to y equal to z. Okay, so we can put the other as well. Okay, of course, here it's all in Z3, right? So the addition is in Z3. So of course, if x equals y equals z, then I have that this is the case. But it should also be the opposite holds. Okay, and so if you just try to interpret this, it's quite simple to see that. So this condition is equivalent to S is an independent set for the following graph. So H cap set tensor N. Okay, so yeah, so the fundamental, I mean, the problem we usually look at in the cap set setting is as N goes to infinity, what can we say about the size of the largest such cap set? Okay, and so the breakthrough in 2016 about this cap set problem by Ellenberg and Gisrit, they showed using the slice rank method is that the Shannon capacity of the cap set hypergraph is at most this number 756 to the power n. Sorry, yeah, thanks. So this is the cap set problem. We've seen that the cap set can be written in this language. Let me talk about the second problem, which was my motivation for this. This is called the finding corner free sets. Okay, so this is about finding sets with no arithmetic progressions. Now we'll be looking for sets that I can put on a square that don't contain a corner. Okay. Okay, so I started with the number on the forehead problem. Okay, so yeah, so this is the name of the problem, so the corner problem. And so the motivation for me, at least, motivated by the number on forehead model of communication complexity. Okay, so what is this? The problem? Okay, we'll consider even a very specific problem. So I imagine I have three parties. Okay, so each have an input, which is a bit string of length n. Okay, so I have my three parties: Alice, Bob, and Charlie. Okay, so why is it called number on forehead? Because unlike what you might expect, is that each one has its own input. Here, each player sees the other two inputs, but not his own. Okay, so Alice, who's here, sees Y and Z, but not her own X. And okay, so each one has this input, and they would like to compute some function of these three variables. And okay, so the objective would like is let's call it Eval Z2n of X, Y, Z. They would like to compute whether if I add up X and Y and Z, I get 0 or not. Okay, so is equal to 1 if X plus Y plus Z is equal to 0 and 0 otherwise. Okay, so my objective, yeah, so their objective is to communicate using some protocol. Okay, and at the end, they should all know whether X plus Y plus Z is equal to 0 or not. This is the question. And the question is how much communication they need to achieve this task. Okay, so of course, okay, I didn't specify exactly the model here. It doesn't matter so much, but imagine they have a common board and they can write on this board. Everybody sees what is written on the board. Okay, and so, of course, the obvious thing is if, for example, Alice writes Z on this board, then at least so then this person, like Charlie, will see X and Y and Z on the boards, and so it will be able to determine this property. Okay, so n bits, or n plus 1, if you want everybody to know, n plus 1 bits of communication are sufficient here. Okay. The question is this the best protocol? Okay, is there something which you can do which is smarter in such a way that they can determine this property? So this, you can think of it as a generalization of the equality problem for two parties. Okay, so if you have two parties, I mean, the first problem you learn when you do communication complexity is the equality problem, right? To whether x is equal to y, and the first lower bound you see is that this actually needs n bits of communication. So this trivial protocol is the best you can do.
But why did you say n plus one?
So it depends on the convention on whether you want everybody to know the outcome. Okay, so yeah, the protocol I mentioned. So this guy would know the outcome, but not necessarily all the others. So you would need plus one bit to just write this.
Players trust each other, right? It's like a collaborative setting.
Yes,
Yeah.
yes, yeah, of course, yeah. Okay. Okay, and so yeah, the question is, in this more general model, can one show a similar lower bound? And notice, okay, one other comment about this specific function is that it's actually quite easy if you're allowed to do a little bit of error. Okay, you see that it's quite easy to solve this problem, right? So I mean, basically, each one of them will compute a hash of his bit string and put it on the board, and in this way, you'll be able to determine equality using a constant number of bits of communication. Okay, with a small error. Okay, and so. Yeah, so a further motivation to show a lower bound for this problem is to give a separation between randomized and deterministic communication complexity, which is unfortunately unknown in this model, except if you're allowed to do non-explicit functions. I mean, it's known by some counting argument, complicated counting argument, that there exist such functions, but explicit functions it's unknown as far as I'm aware. Okay, and this is a very natural candidate. Okay, so really the question is, do I need a linear number of bits of communication in order to compute this? And yeah, okay, maybe another remark for those who haven't seen this model before is that this model is actually quite strong in the sense that, and this is the reason it's hard to prove lower bounds, because there is what makes it hard is the overlap of information. Because so, for example, y is seen both by Alice and by Charlie, right? And this makes it quite powerful and makes proving lower bounds hard. And so, yeah, so you can say that one of the big questions in communication complexity is to prove lower bounds in this model when the number of players is large. Okay, so for example, if you are able to give an explicit function for a number of players which grows polylogarithmically with this n, then this would give a breakthrough in circuit complexity. Okay, so yeah, so this model is something that we don't have very good methods for, and we even see it in just for 3 parties for this basic problem.
So again, so polylog number of players, and then
yes, and you need to show a lower bound, which to get. Okay, so yeah, if it's polynomial, I think it would give already a lower bound. So any polynomial. I think okay, so it has to be relatively explicit in the sense that you cannot encode too hard stuff in there, but yes, it would give you a lower bound for ACC 0, I think. Okay, so. Okay, so how is this related to Shannon capacity? So let me mention now, this is mention this as a proposition here. So yeah, I'll claim in this proposition that this question is exactly a Shannon capacity question for some fixed hypergraph, which I'll call the corner hypergraph. And knowing whether this quantity is linear in n or not is exactly will be exactly about deciding whether the Shannon capacity of this fixed hypergraph is equal to is full. I mean, it's the maximal value. Okay, so and yeah, but I should say that this method is really quite old. From the, I mean, basically this statement is basically, you can see it in the original paper that defined this model by Chandra, Furst, and Lipton. Okay, it has been slightly improved and generalized in later papers, but it's basically the same ideas. So let me just write it this way. So deterministic. I'll write it like this: communication complexity of Eval Z2n. Okay, so n log 4 over theta of h core plus little o of n. Yeah, maybe I should have just done that. Okay. And here it's the same thing. 4 over theta of h core plus little o of n. Okay, so yeah, so just if we forget the sublinear terms, then you see that the constant here is exactly given by the Shannon capacity of some hypergraph, which I'll define in a minute. So where? Okay, so this is a hypergraph on 4 vertices. Okay, so I write core for corner, and maybe it will be clear from here. So okay, so the vertices, it has 4 vertices, but it's convenient to label them in terms of bit strings of length 2. Okay, and the edges, okay, so I should write core here. Okay, so what are the edges? The edges will be just the corners. So what do I mean by a corner here? So so the first entry, I put the center of the corner. So I put 0, 0. And then I add a 1 in the first entry, and then I add a 1 in the second entry. So 1, 0, and 0, 1. Okay, so this is a corner, if you want to see it this way. So this is 0, 0, this is 0, 1, 1, 0, 1, 1, and the corner is something like this. So, and I have 4 of them. So yeah, 0, 1, and then I add the 1 here, so it's 1, 1, and then so I add 0, 0, and then 1, 0, 0, 0, 1, 1, then 1, 1, 0, 1, 1, 0. Okay, yeah, so this is my hypergraph, and yeah, so this I want to discuss this proposition. It's not so hard to prove. It's using basic methods in communication complexity, and yeah, so we can understand fully the deterministic communication complexity in terms of just understanding what is the Shannon capacity of this hypergraph. And so okay, so I hope this is enough motivation. So I'll try to show you now what are the methods we developed in order to advance the understanding of Shannon capacity in general, and in particular motivated by this specific hypergraph. Okay, so and as I said, I'll start with lower bound methods. Okay, so here lower bounds, okay, so it means constructions of independent sets for large tensor powers, and this gives me communication protocols for this problem. Okay, so yeah, so instead of trying to show here that I have a linear lower bound on the communication complexity, here I can try to show, okay, do I have a slightly better protocol, right? So here my protocol uses n plus 1 bits of communication. I can ask, okay, can I use half times n bits of communication? Okay, and this is what we'll answer now. This guy. Okay, so two members lower bound methods. Yeah, just maybe before getting into the actual result, I can just because before getting into the method, I can tell you, for example, because we just talked about it. So before our work, the best bound of theta was 2.82 something. I think in terms of communication complexity. This corresponds to 0.5 n. And now, with the method I'll present in a minute, can show this is bigger than 3.39. Okay, so in terms of communication complexity, this gives you 0.24n. Okay, and I'm removing the lower order terms. Okay, and so how does this method work? This is actually a very general method and actually quite simple. And it uses a tool which is very common in the context of matrix multiplication. It uses what is called combinatorial degeneration. Okay, so I won't define what combinatorial degeneration is. I'll directly state the theorem of how to get such lower bounds. Start writing the theorem here. Maybe we can call it the combinatorial degeneration method. Okay, so how does this work? So let's HB 3 hypergraph. Okay, so right, so there's an obvious method for finding lower bounds, right? For the Shannon capacity, right, is to take a finite power of your hypergraph, okay, and compute the largest independent set for this finite power. Okay, if you do that, then it's obvious. I mean, just yeah, if you have worked a bit with this, it's obvious that this gives you a lower bound on the limit. Okay, and here what this theorem will do is something slightly better. Okay, it tells you that you don't need to for a finite number of copies, you don't need to have just an independent set, but actually an acyclic set is sufficient. And the combinatorial degeneration is exactly capturing this acyclicity. So let me. Okay, so how does it work? So yeah, so I'll find a set S in V satisfying following. Okay, that there exists functions, so U1, U2, U3 from V. Actually, it can even be from S. Okay, so let me just, for simplicity, I'll make it for N on S itself only, such that U1 of X plus U2 of X plus U3 of X is equal to 0 for all X in S. Okay, so if I take 3 times, I apply these functions on 3 times the same element, I get 0. But if I apply it on UX plus U2 of Y plus U3 of Z, I get something which is strictly positive for all X, Y, Z, which is an edge, and of course X, Y, Z in S. Okay, so I put a restriction that, yeah, if I take an X, Y, Z such that I have an edge in my graph, then when I evaluate these functions, I get something which is positive. Okay, and so then what is the okay, I wrote a bit too big, but so the conclusion is that theta of my hypergraph, what did I call it? I call it H. So H is bigger than the size of S. Okay, so this is the, maybe let me write then. We have the following. Okay, so if I can find an S that satisfies these properties, then my Shannon capacity is bigger than this S. Okay, so note actually that it's obvious if I start with an S, which is an independent set itself, then it's obvious that this is satisfied, right? Because I will never have an edge actually. Okay, so this I mean, this condition will not say anything. Okay, but this is a relaxation of this in the sense that you're allowed to have edges. Okay, but in this case, when you sum up these U's, it should give you always something on the same side. So it should always give you something which is positive. Okay, so okay, so here this is the end of the statement of the theorem. So maybe I can say a few remarks. Is that yes? So you can see this if you want this definition as a generalization of an acyclic set. Okay, so if we imagine you have just 2 of these functions, not 3, then what you can see is that this U1 and U2 can be thought of as a relabeling of the columns that make your adjacency matrix into upper triangulars. And yeah, so you can think of this S if you want. You can call this an acyclic set for a hypergraph if you would like. This is I think a valid definition, which when you restrict it to the case of graphs, it gives you the usual notion of acyclic set. Okay, so another simple remark is that, so notice that you can, okay, so this of course will give you a lower bound, but you can, what you can always do is you can take like 2 copies of H, okay, and try to find such an S for these 2 copies, and provided you take this to the power half, it will give you also a lower bound on the Shannon capacity. Okay, and so the way we found this, okay, so the way we found this is just by using this theorem and taking 3 tensor copies. Okay, so already with 2 you get an improvement, but we could even do 3. So we took 3 tensor copies of the corner hypergraph, and we found such a set. Okay, yes, you can check that. Okay, you can solve a linear program which finds you these U's. Okay. And yeah, so this tells you that this is, and yeah, so this gives you this lower bound. Okay, right. Yes.
To for the geometrically interested people to relate it to sort of degenerations, right, of tensors.
Yes.
And I don't know if you, I mean, it's like the Eval case, right? Or the
Sorry?
It's like the one parameter subgroup. Like the combinatorial part
Yes.
is just that I do it in the diagonal basis and I degenerate.
Yes.
And then sort of this I guess the second condition means that I get higher powers of epsilon.
Yes, exactly. Yes. Yes.
So just you know, maybe
Yeah.
for some people it's useful. Yeah, thought about the combinatorial.
And is this specific to an area degree, or can you?
No, this works for generality. This is very simple.
And for graphs, is it something trivial, or?
For graphs, it's I mean, you can observe that indeed for graphs, it's sufficient to have it's exactly the same proof for graphs, and and actually I was planning to do the proof, but I don't know if the chair will let me. So I'm just seeing whether.
Is it still a useful statement for graphs?
Sorry?
Is it still a useful statement?
Yeah, it's still a useful statement for graphs. I mean, it's only useful if you have a directed graph, also for hypergraphs. If the graph is undirected, this is not useful because exactly, yes, because this will be not stronger than this. I mean, so if you try to find such a thing in a graph which is undirected, it will be exactly an independent set. So this is only useful for a directed case.
Then you just have to try and find good direction.
Yeah, yes, exactly, yes. Okay, maybe what I'll do is I'll not write the proof, but I'll say in words how it works. So the idea is if you take such an S, take such an S which satisfies this property, and what you would like to do is in higher tensor powers, you would like to find an actual independent set. Okay. So this is what you will do exactly. Okay, so you take an S, you take higher tensor powers, and so yeah, I take V to the power n, and my set will be constructed as follows: is I'll take all the tuples of n elements which have exactly the same number of each element in S. Okay, so X, you can think of it as a string of length n. This string has a certain number of each character. And so what I'll do is that for each character in S, I'll take it exactly n over size of S times. Okay. So this is a valid set. Okay. So this is a valid set in V to the power n. Okay. You have to show 2 things. You have to say that the size of this set is sufficiently large. And so it's not hard to see that this is of size of S to the power n divided by something which is polynomial in n. Okay, so it's roughly it's roughly of size S to the n. Okay, so it has the right size. And now you have to check that it's an exact independent set. And this is also not very hard. Just by using these 2 conditions, you observe that. And maybe I'll stop here. And so I'll stop here with the proof. I mean, okay, so that I have a little bit of time to mention the last section. So yeah, I can go here. Yeah, so the last section was about upper bounds.
So for graphs, it's the same. If you have an adjacency matrix with an upper triangular submatrix, then if you take a large power, you find a large diagonal.
Exactly. Yes, it's exactly the same. Okay, so for that, it will be useful to define the notion of induced matching. Okay, so this is you can think of it as a generalization of independent sets. So an independent set is a special case of it. Yes, so for that, it will be useful to, again, now in this case, it's useful to put in the, to consider the full support of the tensor, including the diagonal elements. Okay, so I'll just use a notation. Let's call it phi g. This is just the edge set of G union with V or V. Okay, again, this is the support of the adjacency tensor. Okay, so what is a matching? So I say that I have a matching. D it's a subset of phi G such that for any xy in D, they differ in all coordinates. Okay, yes, so if I take two elements, they cannot share even one coordinate. Okay, so this is just a matching, the usual matching, and what we want is an induced matching. Okay, so this is in the sense that there's no other edges, okay, in the part which is induced by D. Okay, so the concise way of writing this is just if D is equal to phi G intersection D1, D2 times D3. Okay, and where these are the projections of D on the first coordinate, second coordinate. So the thing to see here is just that if you take so if you take maybe I'll write it explicitly. Take an independent set. If you take an independent set, then it very easily forms an induced matching.
So it's an equal, right?
Yes.
That's to be very clear.
So yes, my remark is that if S is an independent set, then D, which is just equal to S, where S is in big S, is an induced matching. Okay, but this is only an example of an induced matching. You could have things of completely different forms. So in particular, right? So here, this if I think of my tensor, I look here at the subtensor, which is indexed by SSS. Okay, and I find that this is the identity tensor, or the unit tensor. Here, in particular, I could look at just a subset STU, okay, an arbitrary one, and as long as I find just the unit tensor, this is a valid induced matching. Okay, and so so we can similarly define alpha IM as also the size of the largest induced matching, and also theta IM, if you would like, that of G is equal to this limit alpha IM bar 1 over n. Okay, so this is of course bigger than alpha, and the important observation is that actually all typically the rank methods, they work equally well for induced matching and independent set. They don't really distinguish between these two. Okay, and yes, so these bounds are actually upper bounds on this theta, on the largest induced matching of G. But unfortunately, it turns out that for the corner problem, the largest induced matching for the corner problem is actually 4. Okay, so it's maximal. Okay, and so I mean, if the largest induced matching is the same as the largest independent set, then this problem, the problem that I presented, is actually easy, or okay, in the sense that the communication complexity is sublinear in N. It's not linear. Or in other words, if I would like to prove a linear lower bound here, I need a method which really can distinguish between the induced matching and the independent set. And so, okay, so we try to pursue this a little bit. I can just to pursue this a little bit and try to see whether you can define similar methods than the methods that were used, for example, for the CAPSET problem, for the setting where we're really looking at independent sets and not induced matching. And so in this context, we define the notion of, or maybe I'll just say it in word. We define the notion of symmetric subrank. Okay, so you can think of the method for proving the CAPSET upper bound as based on finding bounds on the asymptotic subrank. Okay, here because we have to use the fact that it's an independent set, it was natural to say, okay, why not replace the subrank by the symmetric subrank? Okay, which is a little bit like the relation between the rank and the symmetric rank, if you want. Because the symmetric subrank is not an upper bound on the induced matching number in general. Okay, and okay, so we try to generalize a little bit the Strassen theory in this setting. We could get some results in this direction, but yeah, we could not solve this question. So it still remains an open question. Maybe the main open question here in this talk is, can one really define, like, generalize the Strassen theory of support functionals, for example, in the symmetric setting and giving you like strictly better bounds? And I'll stop here. Thanks. I think I'm exactly on time. Yeah.
Yeah, well, if you have this question, I guess, do you know of any monotone centering homomorphisms before K at least 3, like generalizations of I don't know, fractional chromatic number to hypergraph case? Or maybe the hammer spawns, you can, I guess, you can look at tensors with entries in the field and see, look at the ranks of that or something.
So yeah, the fractional covering, this works. Yeah, you can also do this. I mean, it's just yeah, it didn't give, it doesn't give, yeah. Yeah, no, it doesn't give anything useful, at least in this setting. Or so yes, indeed, you can the fractional covering number, this would be a valid upper bound on the Shannon capacity, yes, and so, but of course it gives you 4. All of these things gives you, I mean, for the tensor, it gives you what else? And of course, okay, of course, if you use the Strassen support functionals, you get 4, of course. Actually, that's how you prove this, because this tensor happens to be a tight tensor, and so, I mean, this is exactly characterized by the value of the Strassen support functionals, which happens to be 4 here.
We really have a logos theta function.
Yeah, exactly. I think that's the big question. Yes, we don't have a lower theta function for. This would be nice. Sorry, the
Fractional covering number, maybe a hammer span you can use.
Yeah, so that's a bit like using tensors and
yes, yeah,
and then using slice rank, for example.
Yes,
that's a bit like a harness bound.
Yes, but all these, as I said, they I mean,
yeah,
as soon as you have rank, then you have this problem. So you have to, and maybe you use something in between that uses the symmetry, like fractional, doing something fractional and then doing a rank. Yeah, maybe combining these two things could do it. Yeah, but yeah, we couldn't do it.
Oh, nice.
Do you think there could be a way to embed the Shannon capacity problem for larger K into a problem for smaller K? Maybe K equals 3 is in some sense universal or something, like satisfy Boolean propositional logic given the need, well, area degree. This is maybe something like that.
I don't know, actually, because I think actually the K equals 4 version here, even already that, I'm not sure we know that this holds, like, because I think the theorem saying that for tight tensors, that this is equal to the support functional is only known to hold, at least for K equals 3.
So you think it gets more difficult?
Yeah, it might be getting more difficult, yes. And yes, and actually this matches also a little bit with the communication complexity intuition that it does get harder.
Yeah.
I mean, yeah. Yes.
Weird question. So in the k equals 2 case,
Mhm.
like the approximate version of the Shannon capacity problem, which is a useful Shannon
Yes,
capacity,
yes.
it's much easier, right?
Yes.
Is
Yeah.
there an analogous maybe here where you get an easier version, you get an approximate version of the problem?
Like you allow errors, right? That's what you mean by
Right,
approximate.
yeah.
In the communication.
problem, yeah. You put such a-
I guess that's part of the question.
Yeah, yeah. So, I mean, yeah, if I take it very superficially and look at, but okay, it's, I think it's, I mean, the communication, it's not probably not related, but just, so the communication complexity problem that this is related to is actually easy in the, if you allow a little bit of error, it becomes very easy. And not sure this is related to what you're saying, but okay. Another thing which is on a like on a technical level is that I mean, if you look at the capacity of a channel, right? This is something which is additive, okay, or multiplicative if you don't take the log, and so. Yeah, I think it's natural to try to look for quantities which involve some entropies, which would be upper bounds on the independent set, and which have multiplicativity or additivity property. So yeah, this is from a technical point of view. Yeah, if one can define a quantity, even if it doesn't have any interpretation, if it's just it just has this additivity property, this would be.
Okay, thanks.